The Doppler effect is basically refers to a relative change in frequency or the wavelength due to motion of an object. Like example, we have a source which is emitting out radiation or waves, and that source is either moving towards or away. So as you can see the two pictures, one on the left hand side, the source, one on the left hand side, the source is moving away. On the right hand side, the source is moving towards. So what we observe here, this is the observer, the eye. So what observer will receive, as you can see, the source is moving away from the observer. The distance between the two wavefronts increases, or he will receive a longer wavelength. And opposite will happen if a source is moving towards the observer. As a result, what will happen? What is received by the observer, or the radiation which is received by the observer. So what source is emitting out? Like if the source is moving away, or source or observer both are moving away. So as a result, what observer will get? He will receive a longer wavelength. And if a source is moving towards the observer, as a result, what will happen? Observer receive a shorter wavelength what is emitted out from the source. Or we can also say longer wavelength means smaller frequency and shorter wavelength means high frequency. So when the source is moving towards the observer, the frequency which the observer receive will increase and the wavelength will decrease. Whereas if the source is moving away from the observer, the frequency which is received by the observer is smaller, but the wavelength, the distance between the two wavefronts will be larger. So this relative, due to the motion of the source or observer, the frequency and the or the wavelength appear to change, and we call this effect as a Doppler's effect. But what if source and observer both are stationary, or if source and observer were not moving? Example, so we have a source here which is stationary, and we have an observer. Two observers are there. This is a source. Observer 1 example O1 and observer 2 example O2. So the source emit out radiation. Example, source is emitting out a frequency of 800 hertz. But because this source is stationary, source is at rest and observer are also at rest. Observers are not moving. So as a result, what happened when the first wave is emitted out? Like example, this is the first wave which travel equal distance all the direction. Because the first wave will travel a greater distance at it is as it is produced in the beginning, then it will produce a second wave after some time. So this will be the second wave. So this will be the second wave produced, and then after some time it will produce a third wave. So this is the third wave. So when we compare the wavelength, the distance between the two successive wavefront for observer 1 and observer 2, it will be same. What is emitted out from the source? So if I say this is 800, frequency is 800, and example, the wavelength is 2 meter, example. So what is received by the observer 1? They will receive the 2 meter wavelength. The wavelength which they receive, that will be 2 meter, and the frequency which they receive, that will be same as 800 hertz. And observer 2, again, because both are stationary, so the wavelength which is received by observer 2 is same as the wavelength emitted out from the source, and the frequency received, a number of waves received every second, will also be same. So this is not a Doppler effect. But what is a Doppler effect? Doppler effect means it is a relative change in frequency or the wavelength, or and the wavelength due to motion of a source or observer. So as a result, now what happened instead, like in this example, the observer was, or the source and observer both are stationary. So if the source and observer both are stationary, there is no change in the frequency and wavelength. But what if a source start to move, or it can be other way around, or observers start to move towards the source? So example, we are considering a source start to move. So this is a source. Here is observer 1 and observer 2. The wavelength of the wave, which is example emitted out from the source, is 2 meter, and the frequency is again 800 hertz. When the first wave is produced by the source, so this will travel a longer distance. So this is the first wave. Now, because the source is moving, like this is the position where the source produces the first wave, which will travel equal distance all around. So center will be there, the position where the source is emitting out. Now the source is at new position. So source is at new position. The red spot is representing a new position or second position of a source. So when it will produce a wave, the next wave will be according to this. This is the source, position of the source. So next wave will be around this point. Then it produces another as it is moving towards the observer 1. So example, black spot is representing the third or new position of a source, and it also produces a wave. So this will be the third wave. So what we observe here, or what we see, that the observer 1, when he will receive the radiation or the wave emitted out from the source, he will receive a shorter wavelength. Like example, if this was 2 meter, the observer 1 will receive 1.5 meter wavelength. And what about frequency? The source is emitting out 800 hertz, but what observer will receive, it will receive more than 800, might be example 900 hertz. And what about observer 2? Because with reference to observer 2, the source is moving away. So as you can see, for observer 2, what it appears, that the gap or the distance between the two wavefront has increased. So the wavelength will increase. So what observer 2 will receive, it will receive a longer wavelength, and it will have a shorter frequency. Like it is, source is emitting out 800, but the observer will be around, like example, 700 hertz. But this is not the actual frequency, this is the apparent frequency. This frequency appears that the source is emitting out due to relative motion of a source or observer. And what we call this as a Doppler effect. So Doppler effect is simply the relative change in frequency or the wavelength due to motion of a source or observer. So if they are moving towards each other, either a source or observer or both are moving towards each other, then the frequency will increase and the wavelength will decrease. Whereas opposite will happen if the source or observer are moving away from each other, then the frequency which is received will decrease and the wavelength will increase. Then the Doppler effect, using a Doppler effect, we can also calculate a Doppler shift. What is a Doppler shift? So Doppler shift, it is denoted by Z. It can be calculated by the change in the wavelength divided by original wavelength, or it can be change in frequency divided by original frequency. So example, what is a Doppler shift here? How to calculate a Doppler shift? Like the source is emitting out 2 meter wave, like the wavelength of 2 meter, but observer receive 1.5. So the Doppler shift is, it can be calculated, the Z, which is change in the wavelength divided by original wavelength. So what is the change in the wavelength? And this change is always a greater value minus smaller value. It does not depend on which one is smaller, bigger. It is always a greater, larger value minus a smaller value. So when we calculate 2 minus 1.5, so this will be half. So 2 minus 1.5, that is half, divided by original wavelength. Original wavelength means what is emitted out from the source. So that source was emitting out 2. So this is divided by 2. So 2 minus half divided by 2, 2 minus 1.5 divided by 2. So it means that is 0.5 divided by 2, which is equals to 0.25. So, and Doppler shift does not have any unit because it is a ratio. So ratio does not have unit. So Doppler shift of this wave is 0.25. So all the speed cameras, radars, they use this concept of a Doppler shift to calculate the speed of an object. So if if the source is moving away, the wavelength appear to increase, and source is moving towards, the wavelength which receive will decrease. So Doppler radars are there, like for monitoring the weather or air traffic control. Both uses a radar to find the position and the movement of the plane. And both cases they're sending radiation. Like example, how radars can be used to locate the position and to identify whether the object is moving towards or away. Example, a radar is placed at airport, and what this radar will do, it will send a pulse, a small signal. Example, a radar is sending a small signal of a frequency, say 1200 hertz. This radiation is sent, and what will happen, like how we can identify whether a plane is moving towards or away. So example, if the plane is moving towards the source, so as a result, what will happen, when these waves strike the plane, it bounce back. But when it bounce back, it will bounce back because the object is moving towards. So the wave which bounce back will have a higher frequency. So the what is sent by the radar, example 1200 hertz, but what is received, like example 1300 hertz. So using the concept that if the frequency from the object which is moving, if the frequency appear to increase, what is sent, it means the object is moving towards the observer. And same thing, if there is a plane which is moving away from the, so another plane which is moving away, so how it can, we can identify using a radar. So the radiations which are sent to this, that is 1200 hertz, but the radiation will bounce back because the observer is moving away. This is the direction of the motion. So if the observer is moving away, the wave which bounce back, they will have a longer wavelength. As a result, when they will have a longer wavelength, so like example, or shorter frequency, so we send 1200 hertz, but as a result, what we receive, example 1100 hertz. So we can identify that this plane was moving away from the radar. And how much change is there, like the greater the Doppler shift, it means greater the speed at which the object is moving. So when we calculate a Doppler shift, the one which show a greater change in Doppler shift means that is moving much faster. That's how the speed cameras record the speed of a car, a moving object. And if a driver is over speeding, then the camera capture the image at certain value of the speed. The same concept as like a radar, so sending the microwave which strike the car and bounce back. So if the car is, like example, if there's a speed limit, or if speed limit is there 120 kilometer per hour, but because the car is traveling at a higher speed, so it will show a greater change in this like it will show a great higher Doppler shift will be there, and the greater change in frequency will be there. So that can be used to identify that this car is over speeding, and the camera will capture the image for a car which is moving at a high speed compared to the speed limit. Is it clear, this concept, that how radars can be used? Same concept for monitoring the weather, like identifying whether a cloud system is moving towards or away. We can identify by using this Doppler effect. And these cameras, Doppler speedometers, they're used to identify the speed of the car. So the Doppler effect is used to measure the speed of a moving vehicle. Basically what happened, they send the radio wave of a frequency is sent to the from the speedometer to the targeting vehicle, like their focus. So they send these radio waves as the vehicle, if it's moving, even it is moving towards or away, that does not make difference, because it is using a concept of a Doppler shift, which is a change in wavelength divided by original wavelength. So the change in wavelength can be for object moving towards or away. So the pulse which is reflected from the vehicle back to the speedometer, the shift of the frequency reflected wave is proportional to speed. Like if there's a greater shift, it means the car is moving at a higher speed. Small shift is there, like small change in the frequency, it means the car is moving like relatively, like if there is no shift, it means the car is stationary. There will be shift if the car is moving, but the change in the frequency or the change in the wavelength is directly proportional to speed at which the car is moving. So greater change means greater speed, and at a certain limit, speed limit, the camera will capture the image. Then what is the concept of a red shift? So we have the visible light, which include violet, indigo, blue, green, yellow, orange, and red. Vibgyor, where red is having the highest wavelength and shortest frequency, and violet is having the shortest wavelength and the highest frequency. So it is having a shortest wavelength, or we can say it is having the highest frequency. Now, what is the concept of a red shift or a blue shift? Basically, the stars or galaxies, the major composition is hydrogen, helium, and other elements are there. So example, we are in the lab on Earth. Every element has a unique spectrum, which is called a line spectrum. Like every element is having a tendency to emit out certain wavelength or certain radiation. So example, we are on Earth and we are inside a lab, and we observe that hydrogen is giving out radiation, say 450 nanometer. These are the radiation, the wavelength which hydrogen is giving out in the lab. Then there is a nearby galaxy, or there is a star. So there is a nearby galaxy or the nearby star, which is because major composition is like hydrogen and helium. So that is also having hydrogen. But that hydrogen, when we receive the energy from that galaxy or the star, we observe that that hydrogen which is emitting out the wavelength, or we receive the wavelength, it is like 480 nanometer. So in the lab it appear hydrogen should give 450, but the hydrogen which is emitting out the energy from the galaxy, it's 480. So it appeared that the wavelength which is emitted out from the source, the wavelength has increased. So if the wavelength has increased, what I can say about this galaxy, where it is moving, towards or away? The wavelength which is emitted out from this galaxy appear to have increased. So which direction it is moving, towards us or away from us? So when the wavelength increase, the source, it means that is moving away from us or going away from us. So it means this galaxy is moving away from us. And whenever galaxies are moving away from us, what we call this, we call that as a red shift. So most of the galaxies are around us are moving away from us. So that's why we conclude that the universe is expanding. Redshift means there is an increase in the wavelength because red is having a longer wavelength. So as you can see, red is having a longer wavelength. So it appears that this galaxy is moving away. But not all the galaxies are moving away. There are some galaxies which are moving towards us. So the example, there is another galaxy which is also having hydrogen and that is emitting out radiation, and that radiation which we receive, it is a shorter wavelength. Like example, in the lab it is 450 for hydrogen, but here this galaxy is giving 430 nanometer. So what does it mean 430 nanometer? It means this galaxy is moving towards us. So when the galaxy is moving towards us, we can say that the wavelength will decrease. There will be a decrease in wavelength. And when there's a decrease in wavelength appear, what we call that as a blue shift. Blue shift refers to there is a decrease in wavelength, and red shift means there's an increase in wavelength. So we have violet, indigo, blue, green, yellow, orange, and red. So if we red shift means the wavelength increases, whereas blue shift means the wavelength which we receive that has decreased. So most of the galaxies are giving a red shift, that we conclude that the universe is expanding, but not all of them. There are galaxies which are giving the blue shift, or the wavelength which we receive from these galaxies appear to have decreased. So it means they are moving towards us. Is it clear the concept of red shift and blue shift relating with the Doppler effect? So the hydrogen is emitting out the same energy, but because it is moving towards and away, so due to the relative motion, it appear to have a red or a blue shift. Then a pulse echo technique. What is the concept of a pulse echo technique? So to detect the position of an object, to detect the motion of an object, we can also use a pulse echo technique. On what principle this technique based on? So simply like a reflection. So we have an object, we want to find the distance between the object and the source. So this is an object and we have a source. So we send a pulse. Pulse means a small signal. Why we use a pulse, not a continuous wave? Because if we use a continuous wave, so it will be difficult to identify the wave which sent and the wave which is we are receiving, because we are continuously producing a wave and we are receiving the wave as well. So it won't be effective because we cannot distinguish between the wave which we are sending and receive. So whenever we are using a pulse echo technique, we always use a pulse. Like we send the pulse that strike the object and then we receive that pulse back again. To know the distance between the source and the object or the observer, so if we say distance between the source and the object is d, So we have the formula speed is equals to distance over time. But because in a pulse echo, the wave send and then wave bounce back, so the distance travel will be 2d divided by t. So if we need the distance, so speed multiplied by time divided by 2 will give us the distance between the source and the object or observer. So in a pulse echo technique or reflection, or also known as echolation, we send a pulse and we record the time interval for a pulse to send and receive. If we know the speed, like example, normally we use like radio waves or a microwave, so we know their speed in air, which is 3 exponent 8. So using the speed and time it take to return back, we can work out the distance between the source and the observer. Then there is one thing which is known as a detail of the image in a pulse echo technique, or image detail. So what is the image detail in pulse echo technique? Image detail means like how much distance the pulse travel uh, when it bounce back. That is known as the image detail, or the number of the position the pulse has reflected. That is also known as the image detail. So example, or also known as the length of the pulse. So length of the pulse is also known as the image detail. Basically what happened, like you have an object, identical objects are there, two identical objects, and say they have the total length of 2 meters, both of them. So this is 2 meter, this is also 2 meter. And we are using a pulse, we have two pulses, like we are using a pulse, length of the pulse, say example 0.5 meter. And another one, length of the pulse, say example 1 meter. Now what will happen when this pulse is sent? So when this pulse is sent, first part of the pulse will reflect from the surface, because when it changes the medium, the part of the pulse will reflect. Then what will happen? When the pulse completed one cycle like 0.5, then the part of the pulse will be reflected. So after completing one cycle, the part of the pulse will bounce back. Then after completing another 0.5, the part of the pulse will bounce back. Then after completing another 0.5, the part of the pulse will bounce back. Then another 0.5, which is about 2, make it 2, the part of the pulse will bounce back. Or if the medium change, mostly bounce back. So how many points are there where the pulse has bounced back? Like example, this is point 1, the red spot, point 2, point 3, and point 4. So there are 4 points from which the pulse has bounced back. But if I use a longer pulse, example, I'm using a 1 meter long pulse. So when it completed, so when the pulse is strike, it will first bounce back from the surface. But when it enter inside, after completing one pulse, the part of the pulse will bounce back. Then after completing another 1 meter, the part of the pulse will bounce back. So what will happen when we check the number of the points where the pulse has bounced back? So this is 1 and this is 2. So which one is giving us a more detailed image? Because 4 points the pulse has bounced back. So this is giving a more detailed image. Like more detailed image means what is inside the object. More detailed picture is there. And this is giving us a less detailed image. So we can say length of the pulse is inversely proportional to image detail. If we are using a shorter, if we are using a shorter pulse, it means we'll get more detailed image, or there will be more points from which the pulse has or part of the pulse bounce back. So if we want to reduce, if we want to increase or get a more detailed image, or want to see what is inside the object, we should reduce the length of the pulse. But it cannot be reduced too much, because sometimes if we reduce the length too much, then instead of being reflected, the pulse is absorbed by the material. So we can reduce the length, but it cannot be reduced too much. So if we want to make a detailed image or more prominent image of the object, then we should use shorter pulse, or pulse with a shorter length. Is it clear, the concept of image detail? Any doubt till this point? So example, this is an example question. An air traffic controller, or ATC, sent out a radio pulse with a frequency of 20 gigahertz to an aircraft. After 0.003 seconds, the system received the pulse reflected back. The frequency which we receive now is 20.00002 gigahertz. What is the distance between the air traffic controller system and the aircraft, and what information about the aircraft can you get? So what is the distance? How we can identify the distance here? Because the air traffic control system sent out a radio pulse, and after 0.03 seconds the pulse has reflected or bounced back. So distance between, so the pulse is sent and then received back or bounce back. So we have the formula speed, because this is a source, like a, this is the radar, and here this is an aircraft. So speed is equals to 2d divided by t, because the pulse is sent and received. So we need the distance, so speed multiplied by time divided by 2. That will give us the distance. Speed, as we send a radio wave, so the speed is 3 into 10 power 8. The time interval for the pulse 0.03 second and divided by 2. So we'll get the distance. So this is distance between the air traffic controller and the aircraft is 450 kilometers. It will be 450,000 meter or 450 kilometers. Then what we can say about the aircraft? This is what is sent. This is a source emitting out from the source, but this is what is received. So we receive a higher frequency. If the frequency which we send and the frequency we receive from the object that appear to be higher, it means the object is moving towards the source or they are moving towards each other. So since because the ATC is stationary, so it means the aircraft is moving towards the radar. Is it clear? This example, like how we work out the distance between the source and the observer, as well as conclude what is the motion of an object. So this was about Doppler effect and pulse echo, because both topics are interrelated, and even exam you will find questions are there which include both topics. So I'll share another link and start the discuss the questions related to Doppler effect and pulse echo. So I'll share another link.